There's a moment every spacecraft must survive. A moment of fire, when a vehicle screams back into Earth's atmosphere at 25 times the speed of sound, the air itself catches fire. The temperature outside the hull climbs to 3,000 degrees. The metal underneath would melt in seconds. The only thing standing between the crew and oblivion is a thin skin of ceramic tiles, fragile, brittle, and absolutely critical. For 40 years, this problem has haunted aerospace engineers. And for 40 years, almost everyone who tried to solve it has paid a brutal price. Elon Musk, the man who landed rockets on floating platforms in the middle of the ocean, once admitted something that surprised the world. He called the heat shield a thorny issue. He said building a truly reusable one had never been done before. Coming from the man who reinvented spaceflight, that was a confession that echoed through the entire industry. But while Musk was wrestling with Starship shedding tiles in the skies over Texas, a quieter company was working in the shadows. They believed they had cracked the impossible. This is the story of how the heat shield, the most stubborn problem in modern spaceflight, may finally have met its match. To understand why this matters, you have to go back to the machine that made every engineer afraid. The space shuttle was supposed to be a triumph. NASA promised America a reusable spaceship that would make orbital travel as routine as catching a flight to Chicago. Instead, it became a logistical nightmare that drained the agency's budget and broke the hearts of the people who flew it. The villain in this story was not the engine. It was not the software, it was the skin. The shuttle was covered in more than 24,000 individual ceramic tiles. And here is the cruel part. Nearly every single one of them was unique. Different shape, different curvature, different thickness, designed for one specific spot on the airframe and nowhere else. If a tile cracked, you could not simply pull a replacement off a shelf. You had to machine a new one, custom-made, often costing more than $1,000 before a single technician touched it. Maintenance crews spent the equivalent of 2 human years of labor on tile work for every single flight. The shuttle's annual operating budget swelled to $1 billion. The dream of airline-like spaceflight died quietly inside that number, and the tiles themselves were terrifyingly fragile, as brittle as glass. You could break one with your bare hands. Engineers had to install special strain pads underneath, just so the tiles could survive the normal expansion and contraction of the metal skin beneath them. The reinforced carbon panels protecting the nose and wing edges were even more delicate, vulnerable to any impact. Then came 2003. Columbia broke apart over Texas, killing 7 astronauts. A piece of foam light as a child's lunchbox had struck the wing during launch and punched a hole in the heat shield. The vehicle had no backup, no second layer, no margin for error. The ghost of that disaster still hangs over every engineer who has ever drawn a heat shield on a whiteboard, and the maintenance ritual, it bordered on the absurd. Technicians used a special silicone adhesive that needed 16 hours to cure, plus another 16 hours of manual jack support per tile. After each flight came the rewaterproofing, a toxic chemical treatment using dimethylethioxysilane. Workers wore full hazmat suits. Entire buildings had to be evacuated. The process took days. This was the cautionary tale every modern aerospace pioneer carried in their heart. This was what Musk meant by thorny. SpaceX took a hard look at the shuttle's failures and decided to rewrite the entire playbook. Most of Starship's roughly 18,000 tiles are uniform. Same size, same thickness. Manufactured in flow the way Henry Ford might have wanted them made. If one breaks, you swap in an identical spare. No custom machining, no $1,000 parts. The glue was the next thing to go. SpaceX engineers designed hexagonal tiles that mount onto single metal pins welded directly to the stainless steel hull. A self-locking nut holds each tile in place, and the connection allows just enough movement for the steel underneath to breathe through its thermal cycles. No more 16-hour cures. No more hazmat suits at 3 in the morning. And underneath, they added something the shuttle never had. A secondary protective layer made of an ablative silicone-based felt, designed to sacrificially erode if the primary tiles ever failed. Insurance, the thing Columbia never had, but Starship has its own demons. During early test flights, tiles fell off the vehicle like scales shedding from a fish in shallow water. Musk's engineers eventually realized that the gaps between the tiles, originally meant to allow for thermal expansion, were letting plasma slip through during re-entry. The fix had an almost charming name, Crunch Wrap. A flexible, felt-like material that seals the gaps. Flight 10 proved it worked. The areas wrapped showed minimal erosion. The unprotected zones showed angry, visible burns. Geometry helped too. The shuttle had been mounted on the side of its fuel tank, dangerously exposed to debris during ascent. Starship sits on top of its booster, eliminating that pathway almost entirely. The Columbia scenario, in physical terms, has been engineered out of the architecture. Musk has also boasted about the new material chemistry. Larger diameter aluminum fibers woven into silica matrix, closely related to NASA's own aluminum-enhanced thermal barriers. The new tiles, he claims, are twice as strong as the early versions. The black glass coating likely uses molybdenum additives to handle the shock of going from the deep cold of space to the inferno of re-entry in minutes. This is a war Musk is winning, slowly, flight by flight, but it is being won at a scale no human has ever attempted. While the world watched Starship explode and rebuild in fiery cycles over Boca Chica, another team was quietly working in a laboratory in Tennessee. Sierra Space, partnered with Oak Ridge National Laboratory, was not trying to build a vehicle that could survive a return from Mars. They had a humbler ambition. They wanted to fly cargo and eventually people to and from low Earth orbit, and they wanted to do it on a winged spaceplane that lands on an airport runway. Their secret was not a better tile. It was a different kind of tile entirely. Traditional shuttle tiles were essentially refined sand, beautiful at resisting heat but breakable in your hand. Sierra Space and Oak Ridge developed something new. Silicon carbide-based tiles manufactured using advanced techniques at Oak Ridge's demonstration facility. Stronger, lighter, tougher, the numbers tell the story. The shuttle needed more than 24,000 custom tiles. Sierra Space's Dream Chaser uses roughly 2,000. Mostly square and uniform. That is more than a tenfold reduction in complexity. Inspection becomes simpler. Replacement becomes faster. The entire economics of refurbishment changes. For the hottest regions, they developed something called toughened unipiece fibrous reinforced oxidation-resistant ceramic. A mouthful, but the point is simple. It replaces the brittle carbon panels that failed Columbia with a material designed to survive impact, not shatter under it. Sierra Space believes their tiles can survive 15 or more flights with minimal refurbishment. Turnaround in weeks, not months. The exact attachment method remains proprietary, but the philosophy is clear. No more glue horror stories, no more chemical baths, no more hazmat suits, but here is where the story takes its strangest turn. For 60 years, the safe choice in spaceflight was the capsule. Mercury, Apollo, Soyuz, Dragon. A blunt bucket that falls behind a heat shield and floats down under parachutes. It works, it is reliable, it is, in the language of the industry, proven. Boeing's Starliner was supposed to be the ultimate expression of that philosophy. Conservative, heritage, safe. Meanwhile, Dream Chaser with its swept wings and runway landing dreams was dismissed by many as overambitious. A beautiful idea but unproven and probably impossible. Then 2026 arrived, and the script flipped. In February of this year, NASA officially classified the 2024 Starliner mission as a Type A mishap. The same severity classification once applied to Challenger and Columbia. 5 reaction control thrusters had failed during docking. Teflon seals had deformed and overheated. 7 helium leaks had bled from the service module's manifolds. The vehicle that was supposed to be the safe bet had become a cautionary tale. The history is brutal to read. An 11-hour software clock error that prevented a docking attempt in 2019. Flammable tape discovered wrapped around internal wiring. Parachute deployment failures. Moisture-corroding valves. Quality control issues that suggested something deeper had broken inside the program. Meanwhile, Dream Chaser's delays were of a different kind. Sierra Space had chosen a non-toxic propulsion system using high-test peroxide and kerosene instead of the standard but poisonous hydrazine. A noble decision for ground crews and the environment, but one that triggered years of new certification work. The engine had to switch seamlessly between modes. The peroxide had to be stored with absolute material precision or it would decompose. The combustion stability had to be proven again and again. These were the growing pains of building something new. Boeing's problems were the symptoms of failing to maintain something old. NASA noticed. There is one more strange thing about Dream Chaser. The cargo version has no windows. To anyone raised on Apollo and Star Trek, this feels wrong, almost claustrophobic. But the engineers see it differently. Every window is a structural weakness in the heat shield. Every glass pane requires its own thermal protection. Every cutout creates a place where the tiles must work harder. By removing the windows, Sierra Space can wrap the entire nose in a continuous unbroken sheet of ceramic armor. The vehicle sees with high-definition cameras and LiDAR instead of human eyes. The crewed version will likely add some form of viewing capability, possibly virtual screens, but the philosophy is clear. The future is digital. The pilot becomes a passenger of trusted sensors. Coming home gently. And finally, there is the landing, the moment everything has been building toward. A capsule like Starliner drops out of the sky and hits the ground hard, pulling 4 gs or more on its way down. For a healthy astronaut, it is uncomfortable but survivable. For a researcher returning after months in zero gravity with weakened bones, or for a delicate biological experiment, or for someone with a back injury, it can be ruinous. Dream Chaser glides. It lands on a commercial runway at 1.5 gs, no more violent than a normal airline descent. This is the difference between space being an extreme frontier and space being a workplace, a laboratory, a destination for ordinary humans, not just superhuman athletes. This is what NASA sees when they look at the delayed and unproven spaceplane, not failure, a door opening to a new economy. The capsule is proven. But in 2026, proven is not enough if it does not lead anywhere. Sierra Space did not build a bigger rocket, they built a smarter tile, and in doing so they may have finally exorcised the ghost that has haunted American spaceflight for 40 years. The fire is still waiting, but for the first time somebody might be ready for it.